This is the modeling processes of neighborhood change team. I'm Matthew, and on the team is also Devin, Justin, Nitish, Ian, and Jason. And so first I'll give a high-level overview of our motivation and the background. So this began as a manuscript written by Dr. J. Carlos Martinez Mori, who we worked with these past few semesters. And essentially the idea is that transit infrastructure impacts people, of course, in terms of their economic opportunities, the way they travel, where they travel to within the city. And these things are built with, of course, the layout of the city in mind. But we believe what should also be considered is how these transit infrastructures might affect people and how that itself changes the way transit should be built. For example, looking at the Atlanta Beltline, we've seen gentrification, but this isn't necessarily taken into account when designing the Beltline. And so that's why we're using the Atlanta Beltline as a case study, because there's a lot of research going on about it in terms of the statuses of the communities before and after the construction, where it's being constructed, and the fact that it's ongoing. We can see kind of the policy decisions and like the logic behind why they chose to build this here. And the fundamentals of our project is that we're using a game theoretic algorithm to basically simulate what will happen if, for example, the Atlanta Beltline gets completed. And the reason why this is so important is because we're using actual human behavior via game theory to predict what will happen rather than just arbitrarily defined algorithms or qualitative findings. And so a brief overview of how our algorithm works is it's almost like a agent-based model. So we have agent I moves to centroid C, which is like a census tract. And every time an agent moves to location, it observes, okay, how beneficial is this census tract to me? And that can be anything like how many shops are in the census tract, how similar are my neighbors' socioeconomic status to myself, etc. And so we see that if the cost is high, then the agents likely will not go there again. And after repeating this thousands and thousands of times, we're able to see, okay, agents of this income brackets like these tracks, agents of this income bracket like these tracks, etc. And so what that actually looks like is throughout the course of the simulation, our agents see that they don't like certain tracks, which is why they're going low and agents do like certain other tracks. And this is exactly the kind of behavior we want to see. And this will tell us how much our agents like the city, pretty much, how much they like the census tracks. And they observe cost as a metric of three things. Is the census tract affordable to me? Do I like the census tract in general in terms of does it have a lot of shops? Is it close to the belt line, etc.? And the third metric is how similar is our neighbor's socioeconomic status compared to mine. And this is just a measure of income. So if they're surrounded by similarly wealthy agents, then they like that census tract. And so these are the metrics by which the agents decide whether they like a census tract or not. And we pull our data from primarily the census. And so first we get the outline of the counties from the census. And then we get the shape of the beltline from OpenStreetMap, and we overlay the beltline onto the census tracts in the counties. And then we get this. So what you see here is the agents moving from census tract to census tract over and over again. And over time, they'll center around census tracts which they like, which we can see the beltline, which is marked by these green dots, have the most agents, which is exactly the behavior that we want to see. And I'll hand it off to Jason for details on the implementation.
Yeah, so one of the things that we worked on this semester is spatial smoothing and updating our community score. So essentially, spatial smoothing is the process of like reducing the geographic noise by incorporating information from surrounding areas. Matthew, can you switch back to the PowerPoint? And it's used to like reveal the underlying spatial influence that isn't necessarily shown when you look at the raw data. And how we implement this spatial smoothing is we use a queen contiguity weight which essentially is a binary matrix that is used to define the neighbors for each tract, and it tells you the weights of each tract surrounding the one you currently want to look at. And we use it to compute a smooth value for each region based on its surrounding neighbors' amenity densities. The reason why we're interested in this is our data for our simulation is pulled from OpenStreetMap, which is it often contains regions where there's zero amenity data at all due to OSM being community sourced. So since our agent-based model relies on like a realistic amenity environment, these raw zero values would misrepresent the simulation space. So we use spatial smoothing to kind of create a more realistic and plausible amenity values for our simulation. And one thing that we also worked on is a simplified community score. We'll kind of talk about the community score later, but essentially the simplified community score kind of derives the same spatial logic where the community score for endowment is derived from the difference between the agent's endowment and its neighboring tract's endowments. And here's kind of a picture of our before and after smoothing. If you look at the graph, like those gray areas in the before represent places where there was zero amenity data from OSM. And after our smoothing, we can see that each tract kind of reflects the influence of its surrounding tracts. And just a quick like update, we worked on the front end to kind of make it easier to run our simulation because originally it was a CLI Python application. And was just to help like streamline the process and make editing configs and inspecting outputs easier. It's built on a lightweight Electron desktop wrapper with a React front end, and yeah, that's about it for the front end. We just have we're plans for the future, maybe next semester or future semesters. Just add support for like policy creation. We aim to make the simulation setup a lot more intuitive and easier, and yeah, just make it more interactive for researchers.
So to give a recap on spatial autocorrelation, what it is and why we're using it, spatial autocorrelation finds clusters of similar values in a geographic area. For us, the values we're using is endowment. We've talked about is income, and the geographic area is Atlanta. Specifically, we're using local Moran's I and local Gary's C as our spatial autocorrelation algorithms. We're using them because the community scores is a measure of how similar an agent's endowment is to nearby agents. And the way these work, these two algorithms work, is they find clusters of similar values, and those are given a high value, and then we can use that to calculate our community score. So to get a high Moran's score, you want an agent to exist in a node with a similar endowment, and you want the agent's neighbors to have a similar endowment. So from the grid, the top left grid is the endowment average, and this is just from a toy model, with our agent having a 0.4 endowment, and the bottom row is the algorithm's visit probabilities, so how likely an agent is to like that. And you can see sort of if you look through it, the agents or the nodes that are hot are the ones that have similar endowments and have neighbors that are similar as well. So specific to the actual model, I have the three pictures. The one on the left is these are the census tracts. The census tract in red is the tract that the agent is currently in, and then the ones that are colored are the tracts we are considering for our Morans. So rather than run spatial autocorrelation on like every track to every other track, which would be slow, we take k nearest neighbors. In this case, we're taking the 20th nearest neighbors to the agent's current tract, and we apply a decay to that. So that's where the color grid comes from. You can see the ones that are closer are brighter, they're more yellow, so those will impact the community score more. So the middle one is the neighbor tracks endowments, and the right graph is the contribution to the community score. So red means that's a tract that has a similar endowment and is thus making an agent more likely to like the current tract they're in because they're near tracks with similar endowment. In additional, we also have a flag to include the agent's current tract in the calculation, which is not standard for Morans, but makes sense for our simulation because an agent living in a tract would consider their current track, like their own neighborhood as well. They don't really consider tracks, and we normalize those values to fall between 0 and 1.
We're 10 minutes FY. Yeah.
Okay, so however, currently this is not in our paper, and explain why. The spatial autocorrelation is meant for tract level calculations rather than agent level calculations, which is what we want. So the current implementation gives every agent within a tract that same Moran score, which is not ideal for our simulation. So for next semester, we will focus on figuring out possible solutions. We have a few, but they are potentially too slow and no longer use the library, which is we will work through it next semester. So instead, we use the simplified community score, which just calculates the average endowments of the agent's current track and adjacent tracks and compares that with the endowment of the agent.
So moving on to convergence detection. So this was another one of the major issues that we faced this semester, which was figuring out how to properly calculate and determine whether or not our simulation is converged. So for a little bit of background, Matthew explained earlier that we have agents that move around in our simulation. And so basically when we talk about convergence, what we mean is that the overall distribution of agents across the geography is relatively stable over time. So it doesn't change significantly. And so we had to sort of find a mathematically rigorous way of determining this. And so what we came up with was to use what's called maximum best action regret, which essentially just means taking the actions that the agents actually took and comparing them to the best actions in hindsight. And so essentially, ideally, this value would decrease over time as our agents get better and better at learning which tracks are more optimal for the cost function. And so you can see these are just some plots that we generated over the semester. You can see that our convergence is going down, which is a very good sign. It suggests that our model is working as intended. It suggests that our agents are learning as intended. There are a little bit of issues with the value that it's converging to itself. For example, like a lot of the theory states that it needs to fall under a certain threshold, but so far we haven't exactly seen that. However, the fact that it seems to be converging to a value and it seems to be stable after a large number of time steps is promising in and of itself. So yeah, there's a lot of limitations to this, but I think we can definitely work with what we have right now, and I think that we've made a lot of really good progress in this.
Yeah, so now I'm going to talk about the calibration model. So calibration is used to essentially get past census data and adjust parameters based on that. The previous calibration model we were using is NSGA2, and it was designed for multi-objective problems, but the issue is that this creates unnecessary overhead because our calibration mechanism only needs a single fitness metric. So doing some research, we decided that a faster alternative would be PSO, or particle swarm optimization. And essentially, this is a method that uses swarm intelligence and velocity updates. So essentially, you have candidate solutions, and you essentially go towards candidate solutions that produce better outputs. And because of that, it has more lightweight operations because unlike other genetic algorithms for calibration, there's not like crossover or like computationally expensive properties. And because of that, it's easier to train hyperparameters because you're controlling less things. And it also allows for easier parallelization. This is because each evaluation is independent. So we changed our calibration model to PSO. Next slide. Just to talk more about what PSO is. So essentially, it's a mechanism where particles move through a formal velocity update equation, and there's like a bunch of different parameters like inertia, social learning, things like that. And so to give more of context, these terms like inertia, for example, it controls like how much momentum there is in like exploration. And like acceleration guides the particles, and there's like just a bunch of other parameters. And so because of this, because there's parameters, we had to figure out which ones are optimal. So we did a literature review, and from there we came to the swarm size being 30 and the generations being 70. I provided some citations in this slideshow that justified the reasoning behind why we picked these parameters. So the implementation is there, but we're running into issues as to a lack of loss going down when it comes to calibration, which I've been currently investigating. But yeah, that's the calibration portion.
Yeah, for our policy analysis, we looked at two levers. We had vertical and horizontal scaling. For now, we're not really pursuing vertical scaling, but we might fully implement and analyze it in the future. Vertical scaling means like we simulate zoning changes in a city to increase housing capacity where it's needed most, and we model this with a linear distance decay function that's shown here. But then like that brings up the question of like how much we should increase density. So we introduced a policy agent, which unlike the resident agents who learn where to live, this agent learns like how to govern the census tracts and like the city as a whole. So the policy agent uses zoning strength, which is kappa, as its action space, and in every simulation it adjusts kappa and observes the resulting aggregate utility, and then uses no regret dynamics to learn the optimal policy that will like help minimize displacement and like maximize satisfaction throughout the city. This graph is just a preliminary result of implementing like the vertical scaling policy, but it's simply a placeholder until we can improve the simulation to improve the results. And in addition to those vertical scaling zoning policies, we also modeled horizontal scaling. This is a counterfactual scenario, and it just asks like what would happen if the entire Beltline loop was finished immediately. And when we do this, we would keep the zoning capacities exactly the same, but just apply high amenity scores to every single area along the planned loop. And then the goal is to test whether spreading amenity access can diffuse displacement pressures or serve to concentrate it in certain hotspots. And comparing these two strategies of vertical and horizontal scaling can help us identify like which approach best preserves affordability and while still maximizing all of the benefits that did come with the Beltline.
Matthew, you're muted. Also, we're at 17 minutes, so
Okay, no worries. I'll wrap this up. There's some strengths and weaknesses inherent in the model, but there isn't anything that don't exist in existing models that are popular and published. So I believe there's sufficient to work with for our purposes. And next step is just to run the calibration, and then once we calibrated our parameters, run the simulation with the policies, and then add them to the paper, which we hope to do in the next 1 to 2 weeks. But yeah, that's pretty much our project.
awesome. Thanks, guys. Yeah, lots of contributions. I want to thank everybody that joined this team this semester and helped out